This problem, we're given the graph of r is equal to 1 plus 2 sine of 2 theta, and we're asked to find the area inside of one of these large loops. So this is kind of like almost like a clown balloon, the kind that, clowns go to kids' birthday parties and come these weird shapes that they make with tying up balloons together. We're trying to find the area of one of these balloons, or one of these loops here. All right, now before we get started, let's kind of see if we can eyeball this. I mean, this is an area, so let's see if we can kind of guess the area just by looking at it, just giving an estimate as to what this might be. All right, now just based on the looks of this, here's a 2 by 2 square. This 2 by 2 square looks like it's about the same area as the shaded area that I see here. And so my estimate, just kind of eyeballing it, is that I'm going to get an area somewhere in the vicinity of 4. Now, that is most definitely not a hard calculation. If the answer turned out to be 3 or 5, I wouldn't be all that surprised. But if I come out the other end with the calculus and I get an answer like 0.1, or if I get an answer like 40, then I know that I've done something wrong and I need to recheck my work. So this is just kind of a way of, confirming or that the answer that I get eventually is plausible. So it's a plausibility check is probably the best way to say it. All right, now how do I find the area in this loop? This loop is enclosed when r is equal to 0. So r is equal to 0 here, it's at the origin, comes back, and then hits r equals 0 again when it passes through the origin. So I need to figure out when r, which is equal to 1 plus 2 sine of 2 theta, I need to figure out when that is equal to 0. Okay, so that means that sine of 2 theta is equal to negative 1/2. Now, the sine of an angle is equal to negative 1/2 when the angle is equal to negative pi over 6. Okay, so if I were to draw the picture here, so here's negative 1 over 2. This angle here is negative pi over 6. Now, there are two modifications that I could make to this. Both are important. I could also add any number of full rotations that I want, and the sine of the angle would still be negative 1/2. The other alteration that I can make is I could look at an angle in the third quadrant. If I kind of take this picture and reflect it over, here my y is 1, here's negative 2. This angle here would also correspond to an angle, to a sine of negative 1/2. So I have this as one option, or corresponding to the picture in blue, I could have 2 theta is equal to negative 5 pi over 6 plus 2 pi n. So those are my two options. If I divide, theta is equal to negative pi over 12 plus pi n, or theta is equal to negative 5 pi over 12 plus pi n. Okay, so let me kind of write this out as a list. Negative pi over 12. Then if I add pi, that would take me to 11 pi over 12. If I add another pi, that would take me to 23 pi over 12, and so on. If I were to have negative 5 pi over 12, that would be over here, a little bit to the left of negative pi over 12. If I were to add pi to that, then I would have 7 pi over 12. If I add another pi to that, I would have 19 pi over 12. And so I have an infinite number of possible solutions going in both directions, and they're kind of interlaced. The pink and the blue ones are just kind of interlaced. Okay, now what about the picture here? Well, it looks like, so one reasonable boundary that I could take would be to look at these two as my boundary. So negative pi over 12 is a little bit to the, in the quadrant 4, just a little bit less than 0. That looks like this boundary here. So this edge here going out this way, this looks like theta is equal to negative pi over 12. And 7 pi over 12 is a little bit more than 1/2 pi. And so this edge here, a little bit past vertical here, that corresponds to theta is equal to 7 pi over 12. And so I'm going to find the area in this region between negative pi over 12 and 7 pi over 12 that corresponds to one of these big loops. The small loop would be from 7 pi over 12 to 11 pi over 12 if I wanted to find the area in one of these small loops. Okay, so the area in question is going to be 1/2 integral from negative pi over 12 to 7 pi over 12 of 1 plus 2 times the sine of 2 theta squared d theta. Okay, so that's the setup of the integral. 1/2 r squared d theta. And my endpoints I figured out by this analysis up here, figuring out places where r is equal to 0, where the curve crosses itself. All right, now everything else in the problem is doing the calculus to evaluate this integral. So up until now, I've only been setting up the integral. All right, now I proceed with the calculation. So equals 1/2 integral from negative pi over 12 to 7 pi over 12 of, okay, so 1 plus 4 times the sine of 2 theta plus 4 times sine squared of 2 theta d theta. Okay, now I can certainly integrate 1. I can certainly integrate 4 times sine theta. For sine squared, I ought to use a trig identity first. So integral from negative pi over 12 to 7 pi over 12 of 1 plus 4 times the sine of 2 theta plus 4 times, okay, so the identity for sine squared theta is 1 minus the cosine of double the angle. So twice 2 theta is 4 theta divided by 2 d theta. So I get 1/2 integral from negative pi over 12 to 7 pi over 12 of, okay, let's see what we get here. So here I have 4 times 1 divided by 2. That's 2 plus the 1 out here. That gives me 3. Plus 4 times the sine of 2 theta. Then I have 4 times cosine divided by 2, and it's negative. So minus 2 times the cosine of 4 theta d theta. Okay, and let me bring the 1/2 inside before I integrate. Negative pi over 12 to 7 pi over 12 of 3/2 plus 2 sine 2 theta minus the cosine of 4 theta d theta. Okay, now I integrate. So I have 3/2 theta. Integral of 2 sine of 2 theta is going to be negative cosine of 2 theta. And the integral of negative cosine of 4 theta is going to be minus 1/4 the sine of 4 theta. And I evaluate between 7 pi over 12 on the upper limit, and the lower limit is negative pi over 12. Okay, now I plug in the endpoints. So 3/2 times 7 pi over 12 minus the cosine of 2 times this is 7 pi over 6 minus 1/4 times the sine of 4 times the angle, which is 7 pi over 3. Okay, now I do it again, except this time with negative pi over 12. So 3/2 times negative pi over 12 minus the cosine of twice this, so negative pi over 6, then minus 1/4 times the sine of 4 times the angle, which is negative pi over 3. Okay, now let's simplify and see what comes out of all this. So 3 goes into 12 4 times 2 makes 8. So 7 pi over 8 minus cosine of 7 pi over 6. That is in the third quadrant, so cosine is negative. The reference angle is pi over 6. So this is negative cosine of pi over 6, which is negative square root of 3 over 2, minus 1/4. 7 pi over 3. Okay, so 6 pi over 3 is 2 pi. That's a full rotation. Sine of 1 pi over 3 is square root of 3 over 2. Okay, that's the first bit. Minus. Okay, 3 goes into 12 4 times, so I get negative pi over 2 times 4 is 8. Minus cosine of negative pi over 6. So cosine is even. The minus can just, this minus sign can just drop away. Cosine of pi over 6 is square root of 3 over 2. Then this minus comes out, so plus 1/4 times the sine of plus pi over 3, which is square root of 3 over 2. Okay, so what do we get? So let me take the first terms off by themselves. So 7 pi over 8, and then minus and minus makes plus pi over 8. Okay, so those are put together. All right, now everything else has a square root of 3 over 2 in it, so let me factor that out. So what's left will be 1 here. Then I factored out square root of 3 over 2, so that what's left is minus 1/4. So here I have a minus, so plus 1 again. And then here I have plus 1/4. Sorry, I got it backwards. Minus times this makes minus 1/4. I knew I was doing something wrong. Okay, so the minus times the 1/4, or minus 1/4 here. Okay, so pi plus square root of 3 over 2. And what's left here? We've got 2 minus a half. 2 minus a half is 3/2. And so finally, we end up with the answer pi plus 3 square root of 3 over 4. And so that's the exact area. Now we recall that our eyeball estimate of the area was approximately equal to 4. If you punch this into a calculator, this is going to be a little bit bigger than 4, about 4.4 or something like that. So our eyeball estimate gave us a plausibility check to say that this answer here is indeed plausible just based on what the picture is.